Hello everyone, and welcome to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. If you have any questions, you can post them on Twitter or YouTube and I'll be there to answer. With that said, let's start by opening the project. And we have to remember where we left off because sincerely I don't remember. But we can just check out. There you go. Okay. So if we compile, let's see what happens. It's happy and it compiles. So we can just say that we open the debugger as well. So we see we can run it this. Alright. So this is the output, and yeah, so we pretty much just make some cleanup and we recover our instruction stream as we got it at first hand, and we added the val instruction with a SIB oprem as well. So I think that's nice. So the thing that we can do now is that, well, there's some stuff that we can do here. We can extract another instruction just as we are doing now, which is probably something good to do. We can start like making some cleanup of the tables, which I mean I don't think, I mean if you have seen, if you have seen the streams, pretty much all this stuff here, even though it's kind of forming, it depends on the way that we make the other stuff, you know. So it's been deformed by the design of the usage code in this case. So we designed the usage code. The usage code pretty much this part here is the one that has been defined pretty much everything, and that's the way it should go, you know. Always start by the usage code and you'll be fine. So in this case we start with that, just and you can see here that explicitly when we go and fetch and we go each by each call, we've been adding stuff, you know, adding SIB functionality stuff, you know, whatever. And every time that we need something different, something more, we just add it, you know. And that's pretty much what we want. We don't want to go and guess what it could be, because that would be problematic, because we will need to see, we will find that it's not what we needed, and we will need to step back and do it again, which is something that it would cost us more time. And in fact, it's something that I did, you know. If you saw the streams, you know, before I don't know, I have here the recordings so I can show you, like just because for fun, you know. Before this video, you know, Disassembling MOV 305, which was the first instruction that we disassemble, we also made some stuff, you know. I mean, it's all the stuff that we have here before, you know, some stuff there. But the approach that we got before this video was that we were trying to do the whole stuff at once, which was impossible, you know. So once I realized that it was not like the thing that we should do, I just stepped back there and remake completely the disassembler, you know, which was the best thing to do, because in that case it was not the thing that was disassembling something, you know. So the approach now that we have is that we just go taking little steps, you know, instruction by instruction, adding the things that it needs to be for that particular instruction just to be disassembled, and that's all. And with that, you know, it all start like, it's like little blocks that are to add together and stuff like that. It's just like it has like this special way that there is not just a stack, but it's a system, you know. We can see them as blocks for simplicity, but you know, they can be mixed as the system needs to, and I think that's really cool. So yeah, I wanted to point that because it's important, you know. I mean, errors is gonna teach you the best lessons, so don't be afraid to fail. I think that would be something important to say. Don't be afraid to fail. Always fail, because that's what you learn from. And yeah, I mean, be used to it. Be used to it all the time. Be used to be losing and failing. Okay, so yeah, with that said, so yeah, let's try to do another instruction. Why not? We have a lot of them. We have some big bunch of tables to choose from. So let me see. I want to find out one instruction that has some kind of operands, you know. It can be, I want some to work with the operands, because that's something that we haven't done too much. So I want some operands that, if you see the stream that we output here, we pretty much will have a simple layout. We use a lot of EAX here, some EBX, ECX, some displacement, some scaling, some immediate thing. Probably I want to see some immediate that gets sign extended. Probably that can be one way to go. Another way to go is to do some RDX prefix. That would be something new, you know. For example, we can do, where's the one by, over here we have the RDX prefixes that are occupied by the decrement instruction. So the decrement instruction is a 32-bit. I mean, this way of the instruction, it's only possible on the IA32, because when we use RDX, that would be incompatible. So I think I like that, because it's gonna define. It's gonna with this set, we can start defining how we can control the disassembly mode, you know, if we are disassembling for x64 or 32, which instructions are available. So I think we can go and think a little bit more on how do we want to do that, you know, because if you think about it, right now, for example, the bound instruction is not even possible. I mean, right now we are disassembling, but we're disassembling right now x64, but a bound instruction is not possible in x64. So that's something that we should do as well. to handle which and which are not those instructions. So yeah, we can go with that. We can go with the push. This is the bound GP, the one we got ARPL. Another way to go, well, that's something that we can do, RDX prefixes and shuffle around that. Another thing we can do is just continue with the add instruction. Right now we well, this is not the most explicit thing. This is the most explicit. Right now we have disassembled 2 of them, but we have, you see here, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 modes of that instruction. So we're missing 20 modes of it. So that's probably another thing to do, and I think that's more the way we want to go. Because you see, I mean, for example, the add instruction has all these flavors. The move instruction has other kind of flavors as well, which are also of interesting, because the move instruction, I believe, is the most flavorful in that sense, which has different register modes, immediate modes, addressing modes. Stuff comes out from the move instruction. So the move can be something to do. We haven't disassembled any move instruction at all, isn't it? So let's see. We go to, what is this? This learning point. I can use this one, I guess. For example, it has this map set thing. Look at this. It's like, well, there are not a lot. I thought we were gonna be more. This is the monitor. So yeah, I mean, well, this has the maps and stuff, and it has the more. So we can use the well, we can use the add in that case. It has several ways to. I mean, it has the operand encoding. It has 4 different operand encodings: a mod rec, a mod immediate, AL, AX immediate. The move instead has a lot more, like 1, 2, 3, 4, 5, 6. Let me put my charger. Okay, so we can use the move instruction to load the CS register. Attempting to do so resulting in by object exception. To load the CS register, use the for jump call return. So there's something important here to think about. Is like branching stuff, indirect branches, far jumps, near jumps, all that stuff that are controlled by the jump, call, or return instructions are something also important to think about. You know, like how to disassemble those. I mean, the linear disassembly probably is just gonna be the same. You know what I mean? It's just gonna, oh, we have a jump, call, return. Probably in the future we can think a little bit more of how to think. I mean, what else can we do with that? But normally, what disassemblers do is just like they try to parse the disassembly output and try to make sense of it. You know, like segment the data information into functions. You know, we have a function, we have other functions and stuff, which is something useful sometimes. It's something good to do. And probably I mean, it's more than useful because probably I mean, right now the code that we are disassembling is inside. We are just thinking like if the code lives as isolated in one code segment, which most of the time it is, but there's other times that the code segment is not gonna be that way. You know, well, the code is not gonna be structured in just one segment. It can has multiple segments that points to other segments. You know, and all those far jump calls, you know, pretty much control the flow of the instruction set. So for example, we can have, if we have imagine if we have two segments, one segment can have a call instruction that calls other part on the other segment, another function there, you know, and that's something to think about because, well, the number of code segments that probably we were gonna, I mean, the P file normally tells you how many segments they are, what type they are, and stuff like that. But for example, we can have data segments that have code information, which is a little bit weird, but yeah, sometimes it is. So that's kind of a problem that we have to try to make. I mean, I don't know. We have to think a little bit more thoroughly about that. For now, we can just think about the same code segment isolation, and that would be pretty fine. But yeah, I mean, it's something like think about, like, hey, you know, I mean, not and most of the time, not the P file information is not gonna be just structured this the way that we would like it to be, you know, like isolated and stuff. You can have bananas in the P file, so that's important, but we're gonna do that later when we are like, when we get more about when we get like at least like the whole disassembly, well, a robust thing there, you know, idea of, once we got the disassembler, at least like the form and the basics. I mean, looking that we have like polished the thing that we wanted from it, we can start thinking about this stuff, like having multiple segments and stuff. And even, I mean, just think about it, because well, I mean, it just expands to the other section. But imagine when you have imports and exports, that's something that we have to think about. Like, when we go out from the, I mean, the linker, let's say we have a DLL. When it gets loaded, we got the link from it. So we don't have the information. Well, we could, just if we read the DLL as well, you know. So if we want the disassembly from there, we have to disassemble it to find the. First, we have to see that we are linking to it, you know, like, hey, we're gonna link it. That's, I mean, if we're doing it Statically it's gonna be easier, because if we're doing it dynamically or explicitly, if the call is implicit, it's gonna be a little bit simpler, because we can just do it at when reading the P file. But if it's done explicitly with a load library call, then it's gonna be a little bit more complicated, because first we will need to find out that call somewhere in the code that we are disassembling, and saying, oh, this function that you're calling, it's called load library and it comes from the kernel or something, and then we will know that it's a explicit call to a DLL, which, yeah, I mean, this is just like me thinking about the future. Yeah, so yeah, just a point to bear in mind, and yeah, so let me put here to do, just because we haven't done like our to-do list here, so we probably want to do that as well. Important Intel instructions for my manual pages. This is just the instruction set summary. This is just like a statement. I can put here. So yeah, only the first instruction in the sequence is guaranteed to delay an interrupt. So we're moving something to the stack pointer, which is the base pointer, and we're changing the stack segment to EAX and changing the stack segment as well, EAX. So here we can say that we can it's just saying for protection, probably. I mean, just for being certain that the interrupt is gonna execute, we have to add another SS or another instruction at least, say. So if you want, this is kind of crazy, but this is kind of cool. If you wanted to mask an interrupt, you can call a move SS something, and that will mask it pretty much, which is kind of funny. But it's so wonky that it just happens once. It's not stackable, you know. We cannot have two SS and just pretend that this is gonna be not interrupted as well. So this will be interrupted because it's just this tells us that it's just assures us that just one SS is gonna signal it. So that means that whenever we make this, no interrupt is gonna be called after this SS gets called. So if we have an interrupt that gets placed when the execution gets onto the move EVP instruction, this will be signal. So we have a specialized instruction that is LSS, offers a more efficient method of loading the SS and ESP registers. Intel Core X 1000 processors branching in all earlier processors. Now I don't remember what the W meant, so we can see it in here. It was on the open. Oh, this is the operation description. Oh, here you go. The letters W within a pair of parentheses denotes the content of the operand will be updated by the processor. Read and updated. Okay. So that means that this is going to be read and this is going to be updated. Read, updated. Updated, updated, updated. And probably this is not read at all. Or probably, yeah. I mean, it has to be read, of course, because if not, it couldn't be possible to get the data. But since it's not a register, for example, immediate probably is not used. We have a map set. We have AL from a map set. We have from the AL, AX, EX, or RDX to a map set in memory. Or we have an immediate to an opcode plus what's this? RD. Probably it's an extended opcode, or is inside the opcode. I don't know. But we have various of them, which are these ones, which are the B0, B0, B8, B8. So we see them. We have B, well, let's see, B0, hold on a second. B0 plus RBIB. RB register byte, register word, register to, okay, yeah, register byte, immediate byte. So this is move immediate 8 to register 8. Then the other is move immediate 8 to register 8. Move immediate 8 to register 8 is the same, but it has an RDX prefix. So probably it sign extends the data not encodable on IA32. Then we have a 16-way, a 32-way, a 64-way, and then we have so it should be 1 byte opcode, isn't it? So we have, oh my god, P0. Here we go, we have a move here, immediate byte into byte register. So we have AL, RAL, IB thing, which is an immediate, which can be AL or R8L, CL or R9L, DL or R10L, BL or R11L, AH or R12L, CH or R13L, DH or R14L, or BH or R15L. So how do you know which one we're using? It depends on the RDX, isn't it? So if we want to use R8, we have to use the RDX prefix. So if the RDX prefix is present, we're gonna go and use the R8L, and vice versa. Okay. These are immediate modes. That's nice. So is that the reason why it was Oh, okay, I got you. It was like, what? It was B0 plus RB? Yeah, because in the table are the whole sets of registers, so that's the way we choose which one we're looking at. Or REX if we get the other way. We also have B8s. Now these are B8s. Now B8s, let me move this a little bit more to here. This is no. Here we have another move, which is the other part of the row. You know, we have B8s, and the B8s. It's just the same idea. Now we have immediate words or double words into word, double or quad register. So it can be any RDX or R8, RCX or R9, RDX or R10, RBX or R11, RSP or 12, RVP or RSI, RDI, R15, and that's all. So that's because we don't have any REX prefix that defines any difference between them, just that whenever we have to go with R64 we need the REXW, so that's the case. In any other case we don't need the REX. The only difference would be the data size or the effective operand size. So the way that we can differentiate between these two are because of the effective operand size itself. So yeah, the move instruction is nice in that case because since it has a lot of encodings, we can just play around with it, see different modes, try to disassemble all of them, and try to find out the way to disassemble all of them, you know. So yeah, I like that. We have read that special considerations. We have the instruction default operation size 32 bits. Use the REXR prefix permits access to additional registers. R8, R15. Use of the REXW prefix promotes operation to 64 bits. See the summary chart at the beginning of this section for encoding data limits. Is this a summary chart? Probably, yeah. So let me just read the operation because I'm really interested into it. And this is another move instruction, but this is from control registers. Which we don't care right now, but it's there. This is the same, but from debug registers, which is nice. Probably later in the future we can do that as well. These are SSC2, SSC2, ABX, 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 ABX. Loading a segment register while in protective mode results in special check annotation described in the following listing. These checks are performed on the segment selector and the segment descriptor to which it points. So if we use the stack segment, this is cool. Do you see this? They move twice the segment selector so the interrupt can be signaled, you know? And then okay, and that's if we were moving to the stack segment, you know, remember that. In the other case, if we load to DSES, FS, or GS, and if it's loaded with a non-null selector, then if segment selector index is outside the descriptor table limits, or the segment is not a data or variable code segment, or the segment is a data or non-conforming code segment, or RPL is greater than DPL, or and the current privilege level greater than the data privilege level, then GP exception. If segment no marker person, then not no an exception. And then else we use the segment selector twice, well, so we can signal interrupts. And then if DSSS, FS, or GS is loaded with no selector, then we pretty much just move it on to it. So if you see there, yeah, now I don't know why they don't do this check-in in here as well, because I mean, oh, okay, oh, no, my bad, this is the descriptor. So yeah, I was like, I thought it was reading the same thing, but no. So yeah, it has to load both of them. So the hidden part of the descriptor and the that it's pointing to it, and the offset, which is the normal thing that you will get. So we have access to the offset, and the descriptor, it's implicitly loaded, well, not implicitly but hiddenly loaded onto the SS segment register. In here as well, another segment register, it loads both of them, and it has a punch, some checks that he has to do to do that. So oh, no, my bad, yeah, no, I see the problem, yeah. It's because it's loaded with no selector, so I thought it was the source. No, if DS had a no selector, no, but it's if it's loaded. So if what we are trying to load is a null, then yeah, we don't have to make any checking. That pretty much makes sense. But if we want to load something that is not null, then we have to make the checking as well. Okay, so there are a bunch of instructions, exceptions. Non-canonical form is made to load SS root no segment selector when current privilege is equal 3. If an attempt so we cannot load a 7 selector when CPL equal 3 to the SS. Okay. So yeah, uh, so let's try to choose one. uh, we have the RMate, and then we have an R8, So we have 88R, 88R. We have 89, 89, REXW, 80A. Move register to RM64. Move RMA to RA, RMA to RA, RM16 to R16, RM32 to R32, RM64 to R64, and move serial extended 16-bit segment register to RM64. These are SRAX. SRAX, it has a particular thing there. Does it mean that it's an extended? I don't know. So we never saw that, those little 3 points. I don't know what they mean. Probably there's a, oh, here it is. It's a note. Okay, so the maps, that's in 64-bit mode, RMA cannot be encoded to access the following byte registers. Okay, so it's the same information we saw on the other, on another part of the ISA. RMA cannot be encoded to access the following byte registers if a RDX prefix is used: AH, BH, CH, DH. Okay. So yeah, we can do that. I mean, we let's do all of them. Yeah, whatever. So let's start by I don't know, whatever. Let's try this one that has the RDX. So that we can see what's gonna happen. So it's an 89 with an R. Okay. Okay. So let's do this one. 89R. Okay, 89. Let's go to 89. 89. So we have it EVGV. Which we know what it means if we remember. It's a modern byte, follows the opcode and specify the operand, preset a general purpose register or memory address. The address is computed from a single register and any of the following balance base and index register, screen factory displacement, and whatever. Okay. And G means the rec field of memory selects a general register. AX AX000. Well, AX is a. Oh, okay. So yeah, I was like, what's this 000? It's the encoding of the rec field. Okay. Okay, and V means that we have a word over required 164 depending on operand size attribute. Okay, so for this instruction itself, remember that move needs to explicitly tell the with a prefix, RDX prefix, that we are going to expand to 64-bit mode. Okay, so if that's the case, let's try to do that. I'm going to encode that for 89. Then we have R let me go a little bit backwards. That was because on the opcode column, indicates that the modern byte instruction contains a register operand and an RM operand. Okay. Okay. Oh, okay. So it's a normal case scenario, you know. It's R, and we have a register operand, so that's the only difference. We have a slash R, B means mod and rec in the mod RAM. If it's a slash digit, then we have only the RM because the rec is used for an extended opcode. Okay, so that's what it means. So I can just look at it and say, well, if that's the case, that means that we have 89 RDX and mod RAM with 2 registers into it, or well, two operands. Not 2 registers, 2 operands. It can be a memory operand, so yeah, so we can construct it as well. So we need REXW. If we remember, REXW can move it into here. We can look at it. This is REX, REXR, REXW. So its RDX comes from 4EH to 4FH. This opcode represents valid instructions in IA32 operating modes and in compatibility mode. In 64-bit mode, the same opcodes represent the instruction prefix RDX and are not treated as individual instructions. The single byte opcode forms of the index instructions are not available in 64-bit mode. Index functionality is still available using modern forms with the same function instructions. Opcodes FF0 and FF1. See Table 2.4 for a summary of the RDX prefix format. Figure 2.4 through Figure 10 show examples RDX in use. Some combinations are prefixed by fields are invalid. In such cases, the prefix is ignored. Some additional information follows. Setting RDXW can be used to determine the operand size, but does not solely determine operand width. Like the 66H size prefix, 64-bit operand size override has no effect. 64-bit operand size override has an effect on byte-specific operations. Yeah, so that's something that we have like found throughout the reading of this ISA, is that whenever we had a byte specific operation, those byte specific operations tend not to override its size in any way. Sometimes it does. Well, I don't know, but we have to find out. For non-byte operations, if a 66 is used with prefix REXW1, 66H is ignored. That's true. If a 66H overrides use with REX and REXW, the operand size is 16 bits. So here's where we can see that the operand size is 16 bits. So yeah, the operand size is 16 bits whenever we use the 66H operand size prefix. and that's the only thing that we can change. We cannot address 16 bits. We cannot have an effective address size of 16 bits on 64-bit mode. Okay. So REXR is ignored for EVX. Yeah. We don't need REXR at all. But it's used only for GPR, SSC, control, or debug register. RXR is another one. Okay. RXX if bit modifies the SIB index field. REX B either modifies the base in the mod RAM field or SIB base field. So it goes with the RM. Operand size determined by CSD. So CSD is the flag in the code segment descriptor. So yeah. So for example, we can do this one, register to register addressing, no memory open, RDX not used. Okay, so let's do this. Where is our instruction stream? So we're gonna put, yeah, 48 means REXW, isn't it? Where is it? We're gonna use this one. We have W is not being passed. We're not gonna use R nor B because we are not gonna use extended registers for now. We just wanna print normal registers, so we're gonna use 48, and this is gonna be 8B, and this is gonna be the mother RAM. So it's gonna be one. It has to be 1 and I want to use this one. This is SIB. And it can be anyone, I guess, doesn't matter. Let's start with RDX, why not? So we can say 11000, and here RCX or RDX can be. So it's gonna be this 0. Okay. And then that's it, isn't it? We have the mod and the RAM. We're not gonna have any extensions. We don't need them right now. We can do another case for that on the report. But yeah, let's play around with that. This is OX. Now this is because we have 11 0 1 0 0 0. That's correct. So the first thing I would like to do is transform this stuff. so we can use it in the same way. We have mandatory prefix RDX percent. Let's see what we have there. We don't do it anymore, we don't do anything there, so we can just say that if now we can just say so we have 40, 41, 42, 43, 44, 45, 46, 47, and then 48, 49, 48, 4B, 4C, 4D, 4E, 4F, and then 50. It's just another story, isn't it? Yeah, it's a push, and then it's a pop, and then it's a okay, so that will be fine. So now we are gonna check that, and then here we're gonna say that operand size override prefix present. Right now we don't have any operand size override prefix. We can leave it like that, doesn't matter. C by data size 64-bit. I size override prefix present. C by data size 32-bit, and so on. Now this is gonna be false. That means that we're gonna get 64, and 64, which it's okay. So if that's the case, then we'll get a mnemonic and stuff like that. Okay, so let's add the entry in it, and I'm gonna say this is a 1 byte of table as well. So 2 byte is just 1 1 2 2. This VM resume, it's so yeah, this has a modern person. It has a rective modem. Let's see. It happens to be it's a Mars, so that means it's going from memory to register, I believe. It's well, it doesn't tell you. It just tells you that it's going from rec to mod. So yeah, this has to be true. Yeah, because if you think about it, the instruction is this one. So we're gonna move RM64 R64. Alright, and then it's something important to mention. I'm gonna no, forget it. So the point here is like, okay, this is true, this is true, memory operand size, don't care about that, it's not gonna be used anymore. register open size. This is used. This is going to be which we can put it effective, because I mean, if you want to use the prefix as we want it, we can just do it the same way, but whatever. Okay, so immediate size, data size invalid, data size invalid, yep, that's invalid, and this is just move string. There you go, we have a move entry. So we can just pretty much do the same thing and start by moving it along. Which I believe, well, it would be pretty much the same, isn't it? So let's see what happens. I don't know what's gonna happen, but let's think that's something. We can crash, it's okay. So let's see. We don't have a monetary prefix. What about the result? We have we have it. Now this is gonna be 8 and 8. I mean, that's correct. Now we're on C byte. That means that we probably want to move C byte as well. You know? So probably just because, yeah. Oh, and I forgot the encoding, isn't it? So let's put first encoding. Maybe this is gonna be 4, and this is gonna be 8B. And that should pretty much do it, isn't it? Yeah, okay. Okay, so let's go here, and right here I'm gonna say that, well, for now I'm just gonna say this plus C by, and that's all we want. You know, it all depends. The mode, yeah, that wouldn't change at all, because yeah, whatever. So 64-bit mode, whatever, we're gonna do that, and that's all she said. Okay. One more time. There you go, there you go, there you go, there you go. Define entry offsets to particular bit fields. We got an entry. Let's see with the entry. It's a move instruction. That's correct. And as such, it's valid mnemonic. Yes, it's a valid mnemonic. And begin operand instruction, you know, fetch memory operand. Let's see what happens here. We should have a rec field. There you go. So the if it is effective, yeah, then we have a effective operand size of 8. We have MMM0. MMM0, that doesn't look right, because we chose, well, let me put it here, move RA, we are moving hold on, we choose MR. That means that on the math we're going to write to memory, so we're to the RM, so this is right, this is red, so this is rec. So the one we chose is EAX, well, RAX and RCX. That's the instruction. Move from RCX to RAX. Okay, that's the instruction. And we have, yeah, that's all she said. So we should get our RAX on the well, first we're getting for memory, so yeah, REX should be the thing. So let's see if we got that thing. Why not didn't get it? So probably I wanna go a little step before. Let's say I wanna rewind. I wanna continue. There you go. Have an effective operand size, index fetch more by. So if we get the rec field is 2 and the arm field is 0, and that's probably correct. Yeah. Oh no, DX, isn't it? Okay, so DX, my bad. So it's DX 2 and reg 0, that's correct. So we are gonna get the RM field because that's what we are looking for. So effective operand size is 8. The info offset is stream. Row index is blah, and offset is stream. Oh yeah, it's because that's the way we got it. So if we want to do it correctly, we should move this one row back, isn't it? Well, just to match it in the way we got it right now, which in the future probably is not going to be this, but for now I'm just going to do it that way. And of course, this is important because, well, even though if we move it into this side, it's not gonna be call. We're gonna, because the problem is that we're using MMX, so MMX is the same size to RAX, so we have to say that we want RAX instead. So even though, well, let me put it back because, yeah, I mean, we'll still need to do something fancier. So in that case, what we probably want is to say, where is it? We could have it on the entry encoded, like, hey, this thing has an REX, because if you think about it, we don't need to compute anything at all for that matter, because in the tables, where's the table? This thing has pretty much everything. It has, if it has an REX, if it has, if it doesn't, the way that it has, if it has an REXW or just the REX, if it's an opcode extension, if it has rec mod field, if it has an immediate data information. And well, this is not the complete set, because if you want to go really fancy, and I haven't gotten to there, but we should go as well. This is that thing, this is a 1 by, this is the REX, this is the rec field, so I can just go straight on to the move instruction, and these they are move register 1 to register 2, and the one we are looking for is the first one, because we're moving from the rec to the mod RAM, so it's this one. So the direction bit is not set, that's why it's that way. So this is 8, well, this is 8, well, 88 or 89. The other is 80, 90, no, A, 8A, 8, 8A and 8, 8A and AB, so we have a B, so we have this one because this is 8 and 8B, but this tells me, oh no, we have this one. Oh, okay, so the encoding is wrong. That was good. Yeah, because this is the one we have, 8, no, this one, 8B, this is 8B, we have 8B for RDX. So yeah, that was the problem. I thought it was a register, but the register ones has to be 8 and 8, or 8B, 8A, 8B, but going from the other direction, you know, from rec 2 to rec 1, which is going from model RAM to rec. That's a little bit weird. Oh, why did we put 8B? We were looking at this one. I was looking at this one, which is 9. Okay, my bad. A little transformation there, which changes the whole story, see? So now this is correct, and the place where we have 8B, it has to be 8, 9. And well, I have to say as well that the RDX present is present, you know, so it's not just defining that we have a 64-bit thing, because that's not gonna tell the story, you know. So the thing that we did before is not gonna do it anymore, you know. When we go and fetch for register operand, we'll then need to do something clever here. and I prefer that the table defines it, because, well, the entry, because the entry has the absolute knowledge of it. So if we say like we get an entry that has this particular case, like AB with a 1 byte thing. Well, the problem is that the entry is not gonna I mean, it can tell us that, but how do we know that we are gonna get that? I mean, we have to pass the RDX, like, hey, we've seen the RDX, please give me some instruction that has that particular RDX prefix in that particular mnemonic, because right now, yeah, because if you remember, I mean, we can just say that we have RDX, and then we have, I don't know, A9, any one of these ones, and it wouldn't know that it's this instruction, and that's pretty much the thing, so so what I can say something like this. Now, if we go this route, we get an entry that has a re-express, and we have an entry that doesn't. Then the effective apparent size is the definitive thing for the register, the information, which in this case is the same. So I prefer to have it this way, yeah, and solve it that way, because if we solve it at first, then the second thing, it would be pretty much done. Of course, the table will expand information, like, oh, we have RDX and stuff, but it's not like the end of the world, I guess. We can have a set of flags and just have that encoded that way, so yeah, so let's try to do it this way. So I'm gonna go to the entry. I'm gonna say we don't need this, and we're gonna say And for now, we're just gonna say, where is it? On the entry, initialize. There you go. And that's all she say. Of course, this is totally janky and we want to do something better, but just bear with me and we will do it on once we print this out. Okay, so we got the mnemonic, we have a move, sorry, there you go. And cbyte should be pointing towards the mother M, which it is. It's the 0. I'm gonna fetch some memory thing here. For register operand, effective operand. So now we have RDX, that's correct. And so then we got the result. And then here we're gonna do the same. And we have RDX, that's correct. Totally correct. We don't have any immediate, that's correct. So there you go. We have our remove RAX, RDX, oversimplified stuff, but of course we have to continue. So let's see if we print the other ones as well. We didn't make any changes at all, so we should get the thing out. So bound EAX, EBX, CCX times 2, EAX, FFS0, OB, AD, OC, OA, FATT, ST0, ST1, FUCOM, ST1, ST0, FLD 00, blah 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 4, that's correct, BM resume, PL line 70, XM1, OA, shield, well we can even match it. We have the matcher. Disassembly bound EAX EBX CCX times 2 at EAX FFF0 B and OA F add ST0 ST1 FUCOM ST1 ST0 FLD 4 VM resume PL line XM0 XM1 OA shield blah 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 03 add EAX blah blah blah, and yeah, that's correct. That's pretty much correct. So yeah, so now we can see that we have a Well, it was super simple thing that we just added there, just an instruction. We didn't make a lot to do, but yeah, on the next stream we will continue with this, and we're gonna make this more robust, add more how do we fetch the REX stuff and that and like that. But it's okay. I like that. So please, I think the stream has ended today. If you have any questions, post them on Twitter or YouTube, and I'll be there to answer. Um, yeah, please make your questions related to the thing we did today, and I'll be happy to answer them. So I would say thank you very much for coming, and I will see you all on the next stream. Take care.